All right, and we're back. So thank you. Just a bit about, let's see, we need to turn off the... Good. Okay, a bit about the exam. As you've seen in an email from me today, the average was around 80%, the median was 84. That's a little bit higher than the previous exam, about in keeping with what tends to happen on this exam, so yeah, well done. Good job. Now, that's exam 3, and I know at least a fair number of students out there are feeling okay about how they're doing, and a fair number of students out there are feeling like, shoot. What did I do? Here's a challenge that often happens in a semester. A student will, for whatever reason, have a really challenging experience and not do well on, say, one of the exams. Perhaps your exam 2 score was like not what you wanted it to be. And the question I often get is, can I go back in time and like redo that? And the answer is, my course policies haven't really allowed that kind of thing. I mean, it's not, I know how it is. My kids, I have high school kids at Mountain View High School, and I know if you do bad on a test, you just go retake the test until you get a good grade on it, and then you're fine. And that's not exactly how I've set up my course. Nevertheless, I have been troubled as an instructor by the sense among some students that if you mess up once, you're just lost. And I know that there are different levels of lostness in your mind. For some of you, if I get a C on an exam, you feel like you're lost. Others, if I get a C on an exam, I'm doing good. So I know that it just sort of depends. Nevertheless, I have been troubled by the idea that if you do poorly on an earlier exam, but do well on later exams, there's no real way to make up for what's done in the past. It sort of seems not Christian a little bit. On the other hand, I know that, and some have said, well, why don't we just have a final where the final is all the marbles? I know that stresses the other part of you out because you want to go into the exam knowing that no matter what happens, you're going to turn out fine. So I've tried to strike a balance between the two, and I've gotten some advice from some colleagues that I really respect. So here's what I'm going to propose. It is a change to the syllabus, but it is one that can only benefit you. Right now, your your final score is dependent on 150 points from study guides and problem sets, which you basically get free for just doing the work, no evaluation needed. And then the remaining 85% are on exams, 20 from exam 1, 20 from exam 2, 20 from exam 3, are we up to too many percents yet? And 25 for the final. There we go. Now that works out decently if you're doing well on all the midterms, and then the final doesn't seem so high stakes because you just got to keep doing what you're doing. However, it doesn't necessarily help if you bomb exam 2 and then would like to still improve. And the fact is you can improve and you can get better at things. So what I'm going to propose is an alternative where if your final exam score, that I will give you the higher of 2 possible grades. One is the grade just calculated the way I told you, and then the other is for all the marbles, your final grade is, final score on the final exam is your grade for the class. What that means is if you did poorly on, no, you don't even have to choose, I'll just give you the better option. So it's not like you're rolling the dice, right? You sent me an email and you're like, hi, Roland, I could totally do this. No. No. You misunderstand me. This is why I wanted to send it out in an email where I could explain and at least edit myself before I say things. No. Suppose, and this is just a hypothetical, but suppose you're generally, on exam 1 and 3, you got in the 80s, but on exam 2, you had a really bad day and you got in the 32% or something like that. This opportunity would allow you to show me, hey, on the final exam I got in the 80s, my score should be in the 80s, and then your score is in the 80s, no questions asked. In other words, I'll calculate your final score in the class 2 ways. One is the conventional way, the other is just your straight up final percentage. You get whichever is higher of the 2. Does that make sense? Are there any perverse incentives or problems with that I haven't detected? I think the way it's set up, this means that if you're doing well in the class, just forge ahead. If you're not, there's an incentive to improve. I don't think it should make the final exam more stressful than it was anyway. And in fact, yeah, go ahead.
How cumulative will the final be?
The final is going to be the same as it always was, which is cumulative. Though when you see it, you will probably think it's more heavily weighted to stuff that's between now and then. Though all of that stuff draws on all of the stuff anyway. Yep. So it's a cumulative final, which means it's going to pay. It's going to pay to fix the things that you've messed up on. And at the end, it allows you to show me that even if you took a little bit longer to learn the stuff, that if you've learned it, you've accomplished the mission and you're on to your next step, okay? I wanted to say this now because I know some of you are playing chicken in your minds with the withdraw deadline and trying to figure out, do I need to withdraw or should I? And this at least gives you one other option. So if you have questions about that, and if I've not been clear enough, I'll try to write it in an email. If you have detected some strange, weird problems with this policy proposal, I'm interested in hearing what you think. The cat's out of the bag, though, so now that I've said it, I am going to provide that opportunity, but I don't think it's going to hurt anybody, and I think it provides a way forward, even if things have been rough so far. Okay? Oh, there's applause. All right. This non-biased focus group says yes, so go ahead. So right now, the final exam is written by me. It's not a national exam. I do have colleagues that set it up relative to a nationally ranked sort of benchmark exam. And those colleagues provide a couple of alternatives. Anyway, that's not relevant to this semester. It'll be one written by me because that was always the plan. Yep. That may be better or worse, depending on your perspective. Yes? Is class canceled the week of Thanksgiving? I haven't thought that far ahead, but no, we'll hold class as scheduled. Yep. That being said, the official format is blended, and the lectures get posted online. You may do with that as you wish. I don't take attendance. I'll be standing here alone, lecturing to the chairs. All right. So, let's go. We got a lot of ground to cover. When we were last together, those of you that were here instead of taking the test or worrying about the test, I could tell you were somewhat overwhelmed by going through squalene to lanosterol. Why am I forcing this? Because it's important, dang it, but also because it's beautiful and it's an illustration of the order that can emerge from chaos. If you have eyes to see, you can see the hand of God in it, because this molecule is literally set up to do what happens to it. And all of the steps make sense based on things you learned in 351. So the problem is the molecule's too big for you to scramble and try to write it down while you're there and looking up at the screen, which is why I sent you out this PDF before, and hopefully you've looked at it. If you haven't, what we talk about will still not make too much sense. You do need to go through it with a pencil and paper yourself, or pen if you want to use a pen. Pencil and paper yourself, but I've tried to make it as clear as we can. Here is squalene. Whoops, that's an eraser. 6 isoprene units labeled with these different colors. We typically number the atoms. 1, 2, 3 is the methyl group, 4, and 5. That's just what I choose. You can choose a different scheme if you want. Bonds that are between individual isoprene units that were present in this squalene molecule are illustrated in red. After this, bonds that we form as part of the process are all going to be in blue, so you can see what we're doing. I redrew the squalene molecule in a way that puts everything close to where it needs to be to form the final product. Again, it's probably worth your time to go in and try to draw it this way yourself, but don't try to do it now, because you won't have time. Here is the epoxide that forms. There's an enzyme called squalene oxidase, and it installs an epoxide in this double bond. Okay, and it's not like using MCPBA. The enzyme uses oxygen and the cofactor FAD that you will learn about later and in biochem. But you could imagine what would happen if MCPBA added an oxygen to this double bond. There's the epoxide. So that's not new. You've seen epoxides before. The epoxide gets protonated, and then what happens next is exactly what you would expect for epoxide opening from 351. When an epoxide is protonated, a nucleophile attacks it at the more substituted carbon. Why? Because the mechanism is still backside attack, so it's SN2-like, but it also leans a little bit in the SN1 direction because the leaving group leaves even before the nucleophile gets close. A buildup of positive charge happens on the more substituted carbon where it's more tolerated. The nucleophile is not water or hydroxide, but the nucleophile is a pi bond. That's new. You've never seen a pi bond act as a nucleophile to open up an epoxide. But it just so happens that we have a pi bond that is the appropriate number of atoms away that it can be close to the epoxide. Atoms that are separated by, two atoms that are separated by 5 bonds are pretty close to each other, or can get close to each other via a sort of 6-membered ring transition state. So what I'm saying is the pi bond between 2 and 4 is close enough to attack carbon orange, carbon 2. Now, you're going to have the epoxide open like this. That sort of makes sense even if the nucleophile wasn't a pi bond. Now that the nucleophile is a pi bond, we have another question to answer, which is the pi bond shared between 2 atoms, purple 2 and purple 4. Which one gets the new sigma bond and which one gets the positive charge? Because, as you saw before in 351, when a pi bond attacks an electrophile, you always have to worry about who gets the new bond with the electrophile and who gets the positive charge. And in general, when you have a choice, you select the new bond to be with the less substituted carbon so that the more substituted carbon can have the positive charge. That's called Markovnikov regioselectivity, just so you know. It's not important, but I'm going to use that term in the lecture to summarize what we just talked about. So your new bond is going to be between carbon 4, purple 4, and orange 2, so that the plus can be on carbon 2. That shouldn't be very surprising. If we draw that, what I've just said is summarized here. That's in the PDF that I give you. Here is the intermediate. Let's erase the blue arrow so you're not distracted. Here's your new 6-member, whoops, that's also an eraser. Let's redo, there we go. Here's your new 6-membered ring, there's the plus charge. That's step 1. Asterisk, because even though I've drawn these as separate steps, as I said to you in the email, they're not. Or they may happen very close to the times that each other happen. As soon as you have this positive charge on carbon 2, notice you have another nucleophile. And notice that it's placed at exactly the right distance to be able to do attacking. That placement of where the nucleophiles are is all determined in the original squalene linear product, because we're talking about where this double bond is between carbons 2 and 4. Zooming out briefly and going back up to the squalene product, that information was embedded in that starting material. That double bond is in exactly the right spot to attack a positive charge that's at that more substituted carbon. The placement of the methyl groups clearly matters, right? That determines where the plus charges are going to be, because the plus charges are more stable on more substituted carbons. So, not a coincidence, it makes beautiful chemical logic sense to have the plus charge here and then to have that carbon be close to the double bond. Because what happens next is nucleophile attacks electrophile, or pi bond attacks positive charge. And again, we're going to have a choice. Do we form the new sigma bond between green 4 and purple 2, or between green 2 and purple 2? And in this case, if we form the bond between green 4 and purple 2, we get 2 good things happen. First, the positive charge can end up on the more substituted carbon. Second, we make a 6-membered ring, and that minimizes ring strain issues. Okay, are there questions about that step? 1 arrow, but we're forming a ring, and the positive charge goes on the more substituted carbon. Yeah?
So, what if the carbon selectivity is contradicts to the 6-membered ring?
So what if, and we'll see this in a later step, Kenny, you're asking, what if when you have, what if you make a bond and it gives you the more stable carbocation but the less stable ring? Or vice versa. What if you make a bond and it gives you the more stable ring, but the less stable carbocation? Those kinds of things will happen in subsequent steps. The answer for why it happens is beyond the scope of the class, and in any case, you wouldn't be meant to explain or predict whether something would happen, but just draw arrows to show how it happened. Even so, it's probably related to subtle differences in carbocation and ring stability that are too difficult to predict. And our cop-out hand-wavy answer, jazz hands, is always the enzyme makes it happen that way. Okay, I saw another hand here. Go ahead. Is there a certain stereochemical configuration? Well, the starting material is not chiral. Okay? The epoxide is. You make one stereocenter in the epoxide. The enzyme would control that by basing on whether or not it adds the epoxide from the top face or the bottom face. Subsequent steps are influenced by that stereocenter and possibly by the enzyme. You're not meant to predict which stereoisomer is more stable. Yeah. And did somebody out here have their hand up? I missed it. No? Okay. Yeah, there you are.
What's like a tactic that you suggest us using in order to redraw a super long molecule like that to a way that we can understand how to...
You're trying to go from here
Yes, how would you suggest we draw?
to here. You weren't supposed to figure out how to do that on your own. I know how to draw. I know to draw it this way because I know what the product's going to look like. So just trust me and practice drawing it this way. Yeah. Okay, what else? All right. Right, so we had the second new bond forming there. Again, Markovnikov regioselectivity. Here is the product. Here is the new blue bond. Probably the stereochemical issue. Notice that this is two 6-membered rings fused to each other with a trans linkage. I think some of you saw something like that in 351, and it was the bane of your existence. That thing is called a transdecalin structure, and it is less sterically hindered than the cis option, so that's probably part of what's going on here. Okay, there's, sorry, occasionally pop culture references. I just said okay, and then I thought that it was similar to the guy. You guys won't know this. You guys ever watch Phineas and Ferb? Do you know the lifeguard character that goes, okay? And then he marries Candace's aunt or something like that. Anyway. Okay. So if you're lucky, I'll do my Heinz Doofenshmirtz impression at some point. But today is not that day. Okay, maybe later. Focus. So you got the positive charge on green carbon 2. It's there because you predicted it would be there because we formed the new previous bond between green 4 and purple 2. Notice that that positive charge is within bonding distance to that pi bond in the red isoprene unit. Here is a case where we're going to make a difficult decision because of the weird head-to-head connection, 5-to-5 connection that was in the squalene precursor between the green isoprene unit and the red isoprene unit. When the red pi bond attacks, if we make the bond between 4 and 2, we get a 5-membered ring. That would give us a more stable carbocation, but a less stable ring. If we make the bond between red 2 and green 2, sorry about that, red-green colorblind folks, next time I'll do better. If we make the new bond between red 2 and green 2, we get a more stable 6-membered ring, but we get the positive charge on the less substituted carbon. It turns out for the steroid molecules that are the consequences of what we're doing now, we want a 6-membered ring here. I don't know whether so the answer is either the enzyme controls it or the carbocations are not as different in stability as we think they are. In any case, what happens here is what I'm calling anti-Markovnikov regioselectivity. That is, we're going to form the pi bond between more substituted 2 and green 2 so that we can make a 6-membered ring, even though that does give us a positive charge on this secondary carbon. Okay? So that's the step, and the new bond we make is here. Oops, that's still the eraser. One of these days I'll figure that out. Here's the new bond we make. So that's now 3 6-membered rings fused together with a positive charge on carbon 4. Lastly, well, not lastly because there's still a lot, but we've almost finished the framework of this molecule. Now notice that red 4 has a positive charge and is close to the pi bond in the blue isoprene unit. Again, we have a difficult choice to make. If we make a new pi bond between blue 4 and red 4, we make a 5-membered ring that's less stable, but we get a more stable carbocation. If we make anti-Markovnikov regioselectivity, we'd make a 6-membered ring between blue 2 and red 4, but we'd have a less stable carbocation. This is why there's no rules to memorize here, because we're going to now make the less stable ring so that we can have the more stable carbocation. That's opposite to what we did in the previous step, where we made the less stable carbocation so we could get the more stable ring. Not a general principle here, but you should just be aware of the issues. So what happens is pi bond attacks the positively charged carbon. We make a 5-membered ring, and then there's going to be a positive charge on blue carbon 2. All of that's summarized here. And behold, the protosterol, okay, there it was. There was my shot at Heinz Doofenshmirtz. Behold, nope, no. Perry the platypus, behold. Yeah, well, Michaelis thinks he does it better, so maybe we'll have a contest. Okay. Anyway, behold the protosterol cation. Now, we're not done yet. You think you're done. You've made the framework of sigma bonds, but the thing that the enzyme is trying to make is called lanosterol or lanosterol. I don't know what the correct way to pronounce it is. And the structures are subtly different. Notice that the 3 6-membered rings and the 5-membered ring are all in place. But if you look carefully, there's some things that are not in place. I want you to focus on the methyl groups and the hydrogens. I'm just going to circle them real briefly in gray. I want you to look at the positions of those 4 groups and notice that they are not where they started. And right away you're saying, I didn't know I was supposed to make all of those things happen at once. And the answer is you weren't supposed to know that. But if you think about individually when groups move with carbocations, we're talking about carbocation rearrangement. And so could you make this happen through a series of sequential rearrangements, which we're going to show you. The stereochemistry here is a clue. Notice that this proton, which was pointing down, is still pointing down here. That means it didn't have time to do anything else other than lean over and go to the next adjacent carbon. Notice that this methyl group here is up. It used to be that one. So this is to get from here, the protosterol cation to lanosterol is just a series of carbocation rearrangements. In general, these are rearrangements that get you from one tertiary carbocation to another. Now, you may be uncomfortable with that, and that's fair because if you took 351 from me, I reassured you saying, I will not ever ask you to predict anything other than a secondary carbocation rearranging to something more stable because of a 1,2 methyl or alkyl or hydride shift. But reality is that you can interchange carbocations of similar stability. And that's what's going on here in nature. So we'll do this one by one. I've labeled the offending groups, the groups that are going to move, according to the color of the isoprene unit they were originally in. Doesn't matter just to keep track. The first is a 1,2 hydride shift from the blue proton, just leaning over with its electrons to form a new bond with a positively charged carbon. It still stays on the same face of the molecule. It's still down. And now the positive charge is here. Yeah, go ahead.
How did we go from that cation to the one where we're doing the hydride shift?
It's the same one.
Well, it
Oh.
Blue 1 to pink 5. So it is the same.
All my drawings, why didn't... Who knew about this and didn't tell me? Okay, my bad. I have to edit the PDF. Okay, yep. Good. Nope, you were absolutely right on that. Is it the enzyme, right? You're absolutely right about that. The correct structure is this one. You okay with that? So this is why you beta test things before you roll them out. What? What else is wrong? Oh, yeah, okay. All right. I think I'm going to try fixing that like this. Nope, not that. Why am I struggling with this? Yes, right? Yeah. That's the one. All right. Thank you for that, and sorry about that. This is why we weren't even attempting to draw it stepwise individually one by one, because there's just too many mistakes that you can make. Okay. We're okay on that? Sorry, folks. Anything else? Any other issues? Was that same thing? Okay, good. That's my, let's see how many more no, not that Mr. Noodle events we can have today. Okay, well, carbocation rearrangement. This proton leans over. You can tell it's in the right place because of the stereochemistry. And it's reasonable because you interchange one tertiary carbocation for another. Then the red proton leans over and rearranges to give you this carbocation. Then the methyl group leans over to give you this carbocation. Lastly, this methyl group leans over to give you this carbocation. Now at that stage, you could imagine continuing to do carbocation rearrangement, but it apparently stops here. And I'm not sure why. Again, the enzyme. Probably there is a basic side chain in the enzyme that is close to this hydrogen. And then as soon as the positive charge gets adjacent to that hydrogen, you do the elimination chemistry, and that completes linosterol. So if you go back to your text and you look at the way they have drawn this, what they've done is not wrong. It's actually right. But they've showed you all of the carbon-carbon bond-forming framework steps all at once. And then they've showed you all the carbocation rearrangement steps all at once. And you might have been tempted to think about, I just need to memorize those arrows. But I want you to understand what's going on. And hopefully, now that you've seen them individually step by step, you can see what's going on. Questions about that overview? I have one. How important is this? Well, I made a PDF and we spent 30 minutes that we shouldn't have spent talking about it, so pretty dang important. How would I write a question about this? I don't know. Good luck. But it would be kind of like the questions that you will have answered in the problem set and study guide for terpene chemistry. What mechanistic steps are reasonable? 1, 2, carbocation rearrangements are reasonable, and so on. Okay. With that, that's linosterol. Now, that is the precursor to cholesterol via 19 more reactions. It's also the precursor to vitamin D, estradiol, testosterone, progesterone, cortisol, all of the steroid hormones, bile salts, all of them have this same core structure of 3 6-membered rings fused to each other and a 5-membered ring. Some people thinking they're being cute, call it 3 rooms and a bath. I don't find that particularly cute. I think it's worth a chuckle, maybe. Just singular, huh? Yeah. But that is the core structure. Now, interestingly, how many of you have heard of prescribing statins for lowering cholesterol? Which step do you think the statin inhibits? None of these. The statin doesn't inhibit any of the steps I've shown you. The statin doesn't even inhibit making squalene. It inhibits a step that's even further upstream from that. It inhibits a step that makes the individual isoprene unit precursors. We didn't talk about that in metabolism. Maybe we'll get there in chapter 27. It's not in your text, but I might want to show it to you because there's a lot of people on statins. Does it wipe out all the terpenes? No, because you can take statin drugs and not suddenly have trouble with your stress hormones or your sex hormones. So evidently it's enough to slow down the process and yet you're fine. Anyway, all sorts of interesting things, but we need to move on to nucleic acids. Yay. So what to do? Let's see. I think you will find the nucleic acids chapter 26, somewhat easy, which is okay. You need a break. But we're going to focus in on structure and function, and there are things I want you to memorize and know. We're going to focus in first on the nucleobases. And the nucleobases are the different parts of the thing that's going to differ from the structure of one nucleotide to another. So the nucleobases are all aromatic. They are heterocyclic aromatic molecules, meaning they have nitrogens in them. So it's actually, and you're going to see that all that business on the exam about is that nitrogen basic or not, actually is going to help you understand why the various nucleobases hydrogen bond with each other and which nitrogens can be involved in hydrogen bonding. So there are 2 classes of nucleobases. There's purines and then there's pyrimidines. You do not need to worry about why those names are the way they are, but you should be familiar with them because your biochemistry text is going to talk about purine bases versus pyrimidine bases, and it'll be helpful to you if you're not like, huh? So to have seen it before is useful. The purine bases are actually larger. The pyrimidine bases are smaller, so smaller name, bigger rings. And they come in the following varieties. You're going to see there's some similarities between the bases and then some differences. So here's the basic structure of adenine. If it were just the base, there would be a hydrogen here. However, this is the attachment point for the ribose ring. So I'm not sure what to do. I think I'm just going to go with squiggly line. If it were just adenine, though, there would be a hydrogen here. So can you live with that? Can you live with squiggly line? Ish. Okay. Fine. Protest it. Draw hydrogen in your notes. I don't care. The next is a 6-membered ring with nitrogens here and here. Notice one thing that'll help you in drawing these rings is the nitrogens are never adjacent to each other. They're always interspersed with carbons. So this is the basic structure of a purine ring. What makes adenine is this nitrogen here. A couple of terms that are useful. This nitrogen here is called an exocyclic amine because it is not in the ring. Now, do you expect that nitrogen to be very basic? Why not? Resonance with the ring, lone pairs adjacent to pi bonds. Good, you're learning. That nitrogen should not be as basic as the other nitrogens in the molecule. How about this one? Is that one basic? No, not basic. That's involved in the aromatic pi system. The rest of these nitrogens have lone pairs in sp2 orbitals, and so they are basic, which is why they call this a nucleobase. one of the things that's going to be really important for you is to be able to identify groups in a nucleobase that are hydrogen bond donors versus acceptors. So we're going to color the hydrogen bond acceptors blue. These are groups that have lone pairs on electronegative heteroatoms and are somewhat basic and can interact with hydrogens via hydrogen bonds. Then there are going to be other groups that we will discover, we'll label them in red, that are hydrogen bond acceptors. These are going to be groups that are electronegative heteroatoms with hydrogens on them, and we'll think of them as sort of acidic. Okay? Yeah?
Which one's the acceptor? I like the acceptors.
This is what happens when you talk while you're not, when you stop paying attention when the words are still coming out of your mouth. I meant donor. So a hydrogen bond donor has an electronegative heteroatom and a bond with hydrogen. A hydrogen bond acceptor is some electronegative heteroatom that has lone pairs on it. And this is the hydrogen bond between the two. So donor, acceptor. Thank you for that. That's helpful. Okay. So let's identify the donors on the adenine ring. Where are they? That nitrogen, that one, and that one. Notably, not this one, because that lone pair is involved in aromaticity, and probably not that one on that nitrogen because it's resonance stabilized with the ring. However, this is a hydrogen bond donor, an NH bond. Now, periodically, I get my donors and acceptors mixed up because my brain is thinking about Lewis acids being electron acceptors and Lewis bases being electron donors, which is why I get confused. You can think of it however you want, but we'll try to stick with this hydrogen bond donor versus acceptor for now. Hydrogen bond donors are groups with hydrogens on them that can participate in hydrogen bonds. And hydrogen bond acceptors are groups with lone pairs on them that can interact with the hydrogens. Got it? I'm going to try really hard, but I'm probably going to screw up on my donor and acceptor. So raise your hand if I do. Go ahead.
So for the H bond donors, are there any examples besides just nitrogens and oxygens?
Hydrogen bonded donors would be NH and OH type bonds. In nucleobases, it's always NH bonds. Yeah.
For the nitrogen with the R group, if that was a hydrogen, would that be a hydrogen bond donor?
If there were a hydrogen here, then yes, that would be, you're talking about this, oops, there's the eraser. If it would be a hydrogen bond donor. Yes, good. All right. Others? Maybe we need a buzzer. Somebody get a buzzer app on their phone, and when I get donor and acceptor wrong, someone just needs to go, eh. And then we'll have a fight about whether I'm actually wrong or not. I don't know. Okay, that's adenine. That's often abbreviated as A, which is obvious. So the next one is guanine. Okay, and by the way, there is a numbering scheme for the atoms in this ring. We're not going to learn it because we don't care, but there is people that are experts sometimes do. So if you need to learn that at some point, you can look it up. The Wikipedia article is useful. Are you ever disappointed when you come to my office and ask me a question and I turn to Wikipedia? Do you ever feel like you're not getting your money's worth when that happens? Okay, this is guanine. Guanine shares the same basic arrangement of sigma bonds and heteroatoms, but the location of the various groups and whether they're donors versus acceptors changes. Guanine has a carbonyl oxygen here at the top of the six-membered ring. This nitrogen is actually an NH bond. Notice that those lone pairs on that nitrogen are now participating in resonance with the carbonyl. They're involved in the aromatic pi system. They are not basic. So this is now an electron donating group. Lone pairs on the carbonyl oxygen are I did it, didn't I? A hydrogen bond donating group. Lone pairs on the oxygen can be hydrogen bond accepting groups. The nitrogen at the bottom of the ring is still a donor, but attached to the carbon, thank you, electron donor, hydrogen bond acceptor, but the carbon between the two is actually now has an exocyclic amino group, which is a hydrogen bond donor. Wait, I'm waiting for the buzzer, but I think we got it right. Okay. So, you can see that though they have the same sort of shape, the constellation of hydrogen bond donors versus acceptors changes. That's really important, folks, because you're looking at the fundamental information transfer mechanism in biology that unifies all of life as we know it. Okay? Even bacteria do this. All right. Those are the two purine bases. Guanine has the abbreviation G. Let's now do the pyrimidines. Pyrimidines are simpler. Yeah.
Was that other nitrogen? Is that also a?
Sure. Yeah, we could. So you're talking about this one, still a hydrogen bond accepting group. Now, I'll give you a preview. It's only this face of the purine that is involved in what's called Watson-Crick hydrogen bonding. The other groups that are donor or acceptor groups stick out into the major and minor groups, minor grooves of double-stranded DNA respectively, and transcription factors actually interact with them. That's a really interesting but complicated part of biochemistry that we won't get to in this class. But it's this sort of edge of the purine ring that is involved in Watson-Crick hydrogen bonding. All right, others? Let's do the pyrimidines. We're not going to be done with this chapter today, but we'll get as far as we can. Let's first there are 3 pyrimidine rings. 2 of them are quite similar. One is called uracil. Uracil is found in RNA. Here's the structure of pyrimidines. It's a 6-membered ring with 2 nitrogens. The one at the bottom is the attachment point. There's a pi bond here, a carbonyl oxygen here, and then a carbonyl oxygen here. The nitrogen in the middle has an NH bond. So, based on what you know, lone pairs on the oxygen should be hydrogen bond acceptors, and the NH bond there should be a hydrogen bond donor. Notably, the lone pairs on those 2 nitrogens are not basic. They are both involved in the aromatic pi system. They're both adjacent to pi bonds, so they're not going to be good hydrogen bond accepting groups. That's uracil. For the related base, which is called thymine, uracil has the 1-letter code U. Thymine has the 1-letter code T. Thymine has exactly the same structure as uracil, only, there's still that thing I forgot. Only thymine has a methyl group. Uracil is found in RNA, thymine is found in DNA. The methyl group makes a difference. We won't talk about why. If you want to know more about that, I'll defer to your biochemistry class. I want you to pay attention to the constellation of donor and acceptor groups. Notice they're identical for thymine and uracil. But I want you to see that this adjacent placing of an acceptor and a donor here could line up nicely with the adjacent placing of a donor and an acceptor over here. And in fact, you'll see, and we'll draw this, A hydrogen bonds nicely with U or with T. And that's the AT base pair. Now let's do, any questions about thymine and uracil? Boring. You could memorize this. Remember, in addition to structure memorization, the thing you want to take from OChem is the relationship between structure and function, and DNA is a beautiful place to do that because you're going to see the changing of the arrangement of 2 groups dramatically influences what they will hydrogen bond with. The last of the pyrimidines shares the basic core structure of two nitrogens in a six-membered ring separated by one carbon, and there's still a ketone here, or still a carbonyl there, but this nitrogen here has a double bond to it with a lone pair on it, and there's an exocyclic amino group here. So you don't want to memorize that you could memorize that A, G, and C have exocyclic amino groups, and that might be useful, I'm not sure. Let's identify the hydrogen bond donors and the hydrogen bond acceptors. Notice the complementary pattern, and this one's called cytosine. It's perhaps named, unfortunately, for reasons you're going to see in a little bit. There's a confusing issue about base names versus nucleotide names. The C base is called cytosine, but notice some complementarity. You have a pattern going from sort of top to bottom, acceptor, donor, donor, and on C you go from donor, acceptor, acceptor. So you can see complementary donor and acceptor groups. Okay, questions about that so far? Yeah.
So for A and U/T, is that lower oxygen not involved?
Right. So for A, you're noticing that A, U, and T have three groups that could participate, whereas A only has two. And yes, the one is, and we need to draw the base pair so you can see which one is the one that's left out, but one of them isn't going to have a partner. This is actually really important if you do oligonucleotide biochemistry, because you would predict that GC base pairs are more stable than AT base pairs, because GC base pairs have 3 hydrogen bonds, AT base pairs only have 2. And this is actually true, and you can measure it in the lab. All right, I think that's good enough for today. So have a great weekend. I will see you Monday. We'll still be on nucleotides.